Welcome to a video series on linear integrated circuits. In this video, we shall see a group activity related questions. So this is related to group activity number 3. So here it was asked INL of a 8-bit DAC with V reference of 5 volt is shown in this table. So this is the INL of a this is actually a 3-bit DAC. This is not 8-bit, this is 3-bit. So you are asked to determine the DNL, the output voltage, and it is assumed that the value of K is equal to 1. So we know that V0 is equal to K times V reference into DI. So data given is 0, 0, 0, 0, 0, 1. The corresponding INL is given for all 8 different combinations because this is a 3-bit DAC. And we are also asked to find what is the offset and the gain errors. Now the DNL and V0 have to be found out with this as the INL for a given input combination of 0, 0, 0 to all ones. So let us try to see how do we get this one. So since it is asked to find the output voltage also, we have actually written what is the ideal voltage, output voltage for a 3-bit DAC with V reference as 5 volts and K is equal to 1. We know that 1 LSB happens to be 625 millivolts. For subsequent bit increment, we are simply adding 625 millivolts, and these are the V0 ideal values. So these are the V0 ideal values, and since INL is given, so I have written the actual value of the output voltage. Now this is since the INL is 0, the output is 0, and since INL is half LSB for 001, so from that ideal output voltage, so the actual output voltage will be half LSB above that one. So half LSB is actually 312.5 millivolts. So for 625 millivolts, I have added half LSB. So this how we are getting 937.5 millivolts. Similarly, for this combination of 0, 1, 0, since the INL is 1, so the output voltage expected is 1.25 volts ideally. Since the actual output voltage is 1 LSB above, to this ideal voltage I am adding 1 LSB, that is 1.25 millivolts, sorry 1.25 volts plus 625 millivolts happens to be 1.875 volts. Now this is the actual output voltage. So from the desired one, it is above by 1 LSB. So similarly for different values, suppose if you just have a look at this one, for 111 we are supposed to have an ideal output voltage of 4.375 volts. Since the actual output voltage is 1 LSB above, so to this 4.375 I have added 625 millivolts, which happens to be 5 volts. Now this is the V0, which is the actual value corresponding to the INL that is being given for this particular example. Now once we are through with the V0 voltage, the actual output voltage, we can certainly find out what is DNL. Of course, we can find DNL in many ways. Of course, you can plot the graph for this INL for the given input, and you can find out from the previous value where exactly the actual output is. You can find out the DNL. Otherwise, we can also find the DNL because now we can see this is the, just try to find out how does this DNL is half LSB. The previous output voltage is 0. The actual output voltage would have been 625 millivolts, but it is actually 937.3 millivolts. If you see the difference of the actual and the desired one with respect to the previous one, the desired one happens to be 625 millivolts. Since it is above by 625 millivolts by half LSB, so this is the DNL is half LSB. So with this as the present voltage, the expected value of the next output is 937.5 millivolt plus 625. So which happens to be because now the actual output voltage is this. If you actually find the difference of the actually output voltage would have been 630. Just a minute, let me calculate. If there would have been no DNL, the actual output voltage of this 937.5 millivolt plus 1 LSB happens to be 1.5625 volts, but actually the output voltage is this much. So this is actually half LSB more compared to this desired value from this plus 625. So that's why it is half LSB. So from this voltage, so see the next voltage happens to be 1.625. So this is 1.5625. Actually the output voltage has reduced compared to the previous one. This was supposed to be this plus 0.625. This is 2.25 volts. So this voltage would have been 2.5 volts, but it is less by a larger value. If you actually find out the difference and divide it by 625, so this happens to be minus 1.5 volts. So since it is less than the desired value, so that's why it is minus 1.5. So similarly, from this value, it was supposed to be 1.875. So from this plus 1 LSB happens to be, suppose if you actually find out 1.5625 plus 625 millivolts, so plus 625 happens to be 2.1875. That is the actual output voltage you are expected if there is no DNL. Since the actual output voltage is 3.75, so it is above by 2.5 LSB. So this way we can actually find out how much is the DNL for this given bits here. Of course, there again, of course, you need to sit exactly find out, okay, from this plus 1 LSB is what thing and what is the actual value, whether it is above or below the desired value or not. So for each and everything you have to find out from the previous value plus 1 LSB what is the actual voltage and what is the desired voltage, by how much it is above or below in terms of LSB we need to put it. The offset error is 0 because the desired output voltage is 0, the actual is also 0, there is no offset error. But when it comes to the gain error, the desired output voltage is 4.375 volts, but it is actually 5 volts. So there is 1 LSB above by the desired value. So that's why the gain error is plus 1 LSB. So let us see what is the next question. So in an op-amp based DAC, how to eliminate the offset error? In an op-amp based DAC means, okay, even though if you don't give any input, if you are getting some output voltage, so that can be certainly eliminated by having by applying a input offset voltage of a certain required value. So this is by providing the input offset voltage at the input of op-amp. Next question is, write the output voltage of the DAC circuit which is shown here for these two combinations, that is 100 and 001. You can clearly see that we have 2.2K, this is 6.6K resistance, and this is 8.8K, and this is 2.2 kilo ohms. So this looks like, okay, since the resistances keep on increasing, so we need to think that this is a weighted R DAC. For a weighted R DAC, okay, let us try to find out what is the solution. For a weighted R DAC, the general expression is minus RF by R into V reference multiplied by B1 by 2 plus B2 by 4 plus B3 by 8. This is in general. But for this particular circuit, so we can write minus RF into V reference. So B1 by the resistance is 2.2K. Here it is B2 by 6.6K, and this is B3 by 8.8K. So let me take out 1.1K, which is common in the denominator. If I take out 1.1K, this is 268. Actually, the weight would have been 248. Since there is a resistance of 6.6K instead of 4.4K, so we are having this as B2 by 6. So this is an error which is being introduced in this resistor. Instead of 4.4, it is 6.6 kilo ohms. So that's why it is B2 by 6 here. So once we are through with this thing, and let us try to apply the combination of the input. B1 is 1 and B2, B3 are 0, 0. So when it is 1 and 0, 0, we have this combination. Upon solving this, we will get it as minus 5 volts. Similarly for 0, 0, 1, so we are making B1 and B2 as 0, only B3 is 1. So this happens to be 1/8 of minus 10 volts, which is minus 1.25 volts. One thing to carefully observe is that the error, which is 6.6k instead of 4.4k, is not reflecting in the output because we are not considered a combination where B1 is considered as 1, since B2 is considered as 1, because 6.6k is connected to B2 instead of 4.4k. Since B2 is not a combination that is being asked, so we are getting the ideal values of the output voltage. So that's why we are not seeing any error. So this is supposed to be minus 5, we are getting it. So this is supposed to be minus 1.5, we are getting it because we have this as 2R and this is 8R. This is 2R, this is not 4R, this is actually 6R. So that's why it is 6 here. Now here the R value is now actually 1.1 kilo ohms. So be careful while doing such type of problems. So you have to actually substitute this as 2.2k. This entire thing is 2R. This entire thing should be 4R. Instead of 4 we have 6. So there is an error in this actual connection. So let us see the next question. A DAC with n is equal to 10 bits has V full scale voltage as a very large nano voltages, and you are asked to find what is V0 if the digital input is 2A0H, that is hexadecimal thing. Let us assume k is equal to 1 and 1 LSB we are supposed to find out. Since n is equal to 10 and V full scale voltage is given as so and so, so you can take out this nano and you count 9 bits here. From here it is 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's why it is 4.99 so volts. So this is the FSV. So we know that FSV, the full scale voltage is given by FSR multiplied by 1 over 1 minus 2 power minus n. So using this we can actually find directly what is the full scale range voltage, which is equal to V reference. So upon substituting this we'll get it as 5 volts. So once we know what is V reference, it is easy to find the 1 LSB, which is nothing but V reference divided by 2 power n. So here 2 power n is 2 power 10. So we'll get the 1 LSB value as 4.88 millivolts. So since the digital value given is 2A0, so I am writing its equivalent binary value. So the position of this is B1, that is 1 by 2, this is 1 by 8, so this is 1 by 32, and all the bits are 0. We have the actual output voltage given by K times V reference into DI, where DI is actually this value. So we actually get the output voltage as 3.28125 volts. So this is the actual output voltage for this n is equal to 10 and for a digital input of 2A0. Let us try to find, okay, what is the next question. We are asked to find what is the 1 LSB for this circuit and what is the output voltage for this combination of the input bits. So 1 LSB, since we know that it is K into V reference by 2 power n. So here n is equal to 5 here. As you can see here, this is 1, 2, 3, 4, 5. Upon substituting, we are getting it as 0.15625 volts. Since Di is given as 01010, upon substituting that, so we get V0 is equal to 1.5625 volts. This is a straightforward calculation. Now here we are asked to find what is the full scale voltage and the LSB and the output voltage for these two combinations. Now as you can see, this is a R2R network. So we carefully observe whether the R and 2Rs are properly placed. So this is R fine, this is 2R, this is 2R, this is R fine, this is 2R, this is R, and these two are 2R, 2R, this is grounded, everything is fine. So we have B1, B2, B3, B4, and the gain is actually 1 plus 100 by 1K. So the actual output, this is the Vs full scale voltage. Full scale voltage is nothing but full scale range multiplied by 1 minus 2 power minus n. So we are getting the value of full scale voltage as 5.15 so, and we can find the full scale range voltage is nothing but VFSR into K. K is actually 1.1, so we get VFSR as 5.5 volts. Substituting this combination of V0 here, so we get the output voltage as 2.75 and 2.06.